Hi, everybody. There was a problem with the video recording in the last lecture. Computer crashed, so I'm re-recording the algorithm part of last lecture. So you recall that last week we were talking about breadth-first search. It's a more organized way to search through a graph to find shortest paths. The depth-first search was. And we needed a to-do list. What are the nodes that we should look at next? The ones we've reached but haven't fully explored yet. And I'm going to call that to-do list the wavefront. So I've made a structure, which just means a class with all of the members public by default, called wave element. And inside wave element, I have what is the node ID or intersection ID of this thing that I have reached but not yet explored. So it's in my to-do list. And because I want to be able to figure out how I got to my destination when I actually reach it, I need to store a little more information. I'm going to store the street segment index or edge ID that I used to get to this node. To make the code a little shorter and cleaner, I'm also going to define a constructor, just takes a node and an edge ID and makes a wave element. And I also need a sentinel value. So sentinel value is a special value that won't occur except in special cases. So I want to be able to tell when there's nothing more. This is the beginning of a path. So if a node is the start of my search, there is no edge that was used to reach it, meaning it's the source, I want to say that it has an edge ID of -1. And I know that -1 will never occur because all my street segment indices go from 0 to some positive number. Now I shouldn't put -1s throughout my code. Instead, I use the define preprocessor directive to basically create a name, no edge, which means -1. So now in my code, I can use no edge. It's going to be easier to read. And that means, well, this edge ID is illegal. There is no previous node. Okay, so that's my wavefront. Storing how I got to a node in the wavefront is necessary, but it's not enough. I also need to, once I pull something off the wavefront, process that node. I need to remember, how did I get to this node? So I have this struct node, and it's storing data at every single intersection. And I'm going to store what I'm going to call the reaching edge. And it's also a street segment index. It's what edge did I use to reach this node? Okay, so I've got this new data. How do I use it? Here's my breadth-first search algorithm repeated here with a little bit of extra code so that I'm going to be able to keep track of how I got to the destination. So let's just walk through this again. We have a linked list of wave elements, that data type that I just created. I'm calling that the wavefront. And I'm going to start my search by pushing into the wavefront an wave element that has the source ID and no edge. Okay, so that's this. It's the start of my path. So my wavefront has node 0, because that's what I've said my source is for this example, and no edge, because start of the path, nothing before it. Okay, then the main search algorithm comes down into this loop. So in this while loop, as long as the wavefront's not empty, I keep searching. I've still got things on my to-do list. Okay, so initially my to-do list, the only thing there is my source. I take that, whatever's at the front, the beginning of my wavefront. So my wavefront is acting as a queue. I put things at the back, I take things out of the front. So I get a wave element that I'm calling cur or current with the dot front operator. And in C++, to take something out of a linked list, we need to do two things. If you want to take it out of the front, we get the thing with this dot front, and then pop front actually removes it, which I want. I want this thing gone. Okay, so there's two lines together. Get what's at the front of the wavefront and remove it from the linked list. Okay, so now I've got this current element, and I want to store at this node 0, how did I get here? Because this wave element is kind of transient storage. I'm going to use it for a little while and then throw it away. So I say nodes, which is a vector of type node. So I've got one for every single intersection in my graph. And I say, okay, for the current node ID, which right now is the source, let's save this reaching edge. So we had it in our wavefront, it was this edge ID, let's just make sure we keep a copy of that. And the reaching edge was no edge, nothing before for this case. So I'm gonna store that right here. Okay, so I store that, and my wavefront is now empty. I've taken that element out of it. I check, am I at my destination? I'm not. My destination is way down here, so I'm not there. So I need to keep searching. So for every outgoing edge of this node that I'm at, I'm going to put it into my wavefront. Okay, and I'm going to put it at the back of the wavefront. So I'm using the wavefront as a cue. Put things in the back, take things out of the front. And I'm using my nice little constructor here. So I just say, okay, take the two node IDs. So for example, this one, and also store the edge we used to get there. So for example, this A. So I'm going to do that for every one of the nodes that I can reach from here. So there actually be two of them. I'm going to do it for both node 1 and node 2. Okay, so after I've gone through this loop, my wavefront now has two things in it. Node 1, and I reached it with edge A, and node 2, and I reached it with edge B. And then I go back, let's erase all this. So I go back to the top of my while loop. All right, and I do it all again. So now I take this node that's at the front start of my wavefront, or this wave element at the start of my wavefront, and I go there. Okay, so I'm off at node 1, not at my destination, so I'm going to go look at where can I get to. I can get to here, so I'm going to put that node 3 into my wavefront, and I'm going to record that I got there through edge E. So that goes into my wavefront. And then I'm going to take the next thing out of my wavefront, which is node 2. So I go over here, and node 2 is still not my destination. I'm going to put this node and this node into my wavefront, and I'm going to record how I got to node 2. Okay, so I record that I got there through edge B, and I go back once again through this loop. Okay, and this repeats for a while, so I'm going to go to node 3 and record that I got there through edge E. I'm going to go to node 4, record that I got there through edge C, and then I'm going to go on down to finally reach node 5, record that I got there through edge F, and I'm done. Okay, so I found this path. So how do I print out the path? Well, my main code would look like this. I would say find the path by calling this breadth first search algorithm. I called it with the source ID and the destination ID, and I just showed you that code. If I found it, I now want to construct the path. Basically, the breadth first search found that there is a path, and for every single node, it recorded which edge did I use to get to that node. That's actually enough for me to reconstruct the path, but I do need to do a little bit of work. Every intersection knows how did I get to this intersection, but it only knows one step. I need to put all those steps together. So I'm going to call another routine that I'm writing here called breadth first search traceback, and I pass in the destination ID so that it knows where to start. So it knows that it's going to start on this node. Okay, and this is going to return a vector of edges, because that's actually what we're asking you to do in milestone 3. So it begins by, we're going to store it in a linked list. Turns out to be convenient because it gives me the operators that I want. In particular, I'm going to be using push front, and push front exists on a list, but it wouldn't be efficient on a vector, so it doesn't exist on a vector. So I make an empty path. And at the very end, I'm just going to return that path. Now I'm supposed to return as a vector, so I'm going to make a function called makeVec from list. It's not a very complicated function. STL has copy functions. You can even make a list by passing in 2 iterators to the start and end of, or you can make a vector by passing in two iterators to start and end of a list. There's lots of ways to turn a list into a vector with not much code. So not going to show you that, but I have this routine, makeVec from list. So if I can get a linked list that represents the path, I'll just convert it at the end. Okay, so what am I going to do inside this code? Well, my path's empty. I'm going to say that my current node ID is equal to destination ID. So I'm going to start here, down at the bottom. Okay. And I actually now know one edge in my path because I know for this node, current node ID, I can just look up in this node's data structure, one element for every single intersection, what was the reaching edge. And I'll call that pre-veg. Okay, and in this case, that pre-veg would be edge F. And now I'm going to loop. Okay, so that was the start of my iteration. While this previous edge is not equal to no edge, which means I haven't gotten back to the start of the path, I'm going to push this previous edge into the front of my path. Okay, so my path now has F in it. And I'm not at the beginning of the path, so I have to keep going. So I get the node at the other end of this edge, which I can do. You've seen in Streets database API how you can do that. So I'm going to get that this previous node here. And from that node, I can ask, well, what's your pre-veg? And it's stored there. This one knows that I was reached through edge D. So I can say, okay, the previous edge now becomes, let's look up in our node's data structure for that node, what edge was used to reach it. And in this case, it was D. Okay. And now we'll go through the loop again. So we'll go back into the loop. We'll find that the edge is not equal to no edge. It's not -1. So we're going to go through the body of the loop. We're going to add D into this path. We're using push front, so it's going to go into the front of the path. And then I'm going to do the same thing again. I'm going to say, okay, my current node is on the other end of this edge D, so it's right here. That's now my current node. And let's get what its pre-veg is, which is this, B. Okay, so it's not equal to no edge. So we go back, we check the loop conditions, not no edge, we haven't reached the beginning, so we're not done. Okay, so let's go through this loop again. And when we go through the loop again, we're going to push this into the path, so B goes in there. We're going to find the node on the other end, which is the source. We get its previous edge. Now, its previous edge actually is no edge. It's this special value. So now we're going to drop out of the loop and go here. Okay, so we have found the whole path. The whole path is in order, would go from B to D to F. So by doing this push front, we've actually got the path and we've got it in the right order. We just have to convert it into a vector. And again, that's not terribly difficult. It's there are a lot of simple functions in STL that will do that conversion for you. Okay, so now we know how to find paths, we know how to return them. Let's just look to see if there are any issues. So, and there is one. So let's look at this slightly more complicated graph. If I do a search from source to destination, looking for the shortest path, I start off with my wavefront would be node 0. And then that's not my destination, so I'm going to look at what it can reach. It can reach node 1, it can reach node 2, so I put those in my wavefront. And now I'm going to pull node 1 off of my wavefront. I'm going to record that its reaching edge is A, because that's how I got there. And I'm going to put that I could reach node 3, so that goes into my wavefront. Next thing, I still haven't reached my destination, so I go back, and I'm going to pull the next thing off the wavefront, which is node 2. Okay, it's not my destination, so I'm going to say, okay, I reached you using edge B, so store that. And let's put what I can reach, which is node 1, into the wavefront. Okay, and then we keep going. So we're going to pull 3 off the wavefront, record the edge we used to get there. It's not our destination, so we're going to put what we can reach from there, which is node 4, into the wavefront. We go back, we pull off node 1 again, because it was in our wavefront. And we're going to actually update the reaching edge. We're going to say the reaching edge is now C, because we actually got here from node 2. So we took this edge this time. So we've updated its reaching edge. We're going to put node 3 back in the wavefront again. Okay. And now we pull off node 4. That's our destination, so we're done. Okay, so we reached the destination. But when we actually do our backtrace routine, you'll find that we got this path. We follow all the reaching edges, we get that path. It's actually not the shortest path. This path has a travel time of 5, 10, 16, 19 seconds. Okay, and there's another path, 5, 11, 14 seconds. Okay, so we really should have taken this path. That's the shortest one, but we didn't. Okay, so what happened? Basically, this node 1 we reached twice. We reached it once through this path, and we reached it a second time through that path. And the second one overwrote the reaching edge. So the later traceback, so it overwrote reaching edge to say C. So it said, this is the last path that came through here, remember that. When we did the traceback, that's the direction we went. And we really shouldn't have done this because it was an inferior path. We don't want to do that. So to avoid that, we need to do a check. We can store in our node data structure the shortest travel time from the source at every node. So every one of these is going to now, every one of them already has one of these node data structure entries. We're going to put a new piece of data in there. What is the shortest time I've ever seen to this node? And I'm only going to process a node, do any updates. I'm not going to update its, the travel time to it. I'm not going to update the reaching edge unless the shortest travel time to it has been reduced. So I'm going to do that check before I do anything. Okay, if I make that change, then you'll see that this works. So we start at the source, we put that in the wavefront. Okay, that's not our destination, so we put the two things that it can reach, node 1 and node 2 in the wavefront. All right, we pull node 1 off first, we record that we got there through edge A, and then we pull we put in node 3 back in the wavefront, because that's what node 1 can reach. Then we pull off node 2, okay, record that we got there through edge B, and it's 5 seconds. And we put node 1 in the wavefront again, because node 2 can reach node 1. Okay, we go look at node 3, we record the time was 11 seconds, and we got there through edge D. And now we're going to pull off node 1 again, because we're reaching it for the second time. But this time when we pull it off, we say, okay, well, our travel time was 10 seconds through this path, and we got here before with a travel time of only 5 seconds. So 5 is better than 10, so we're not going to update it. So we're just going to skip doing anything. And now in our wavefront is node 4 is the next thing. We pull it off, it's the destination, so we're done. And we got here in 14 seconds, and the last edge we used was E. We backtrace, and we find the shortest path. Okay, so we fixed it. And that's it for today. We'll talk about this more this week. But with this new tweak to the algorithm, we now can find shortest paths reliably using breadth first search. Thanks.